Hi, everyone. My name is James Hartig, and I'm a co-founder at Admiral. And I'm here to talk to you about scaling YugabyteDB while maintaining single millisecond latency. So a little bit about Admiral. We help publishers sustain online content through relationships. So we offer a SaaS platform that lets publishers show a registration wall if they want to have people register for accounts on their site, offer subscriptions to users. So if they want to have premium content, or require a subscription to see the site without ads, they can use our platform for that. We also have engagements that kind of underpin the last 2 points, but will really allow a publisher to show some sort of modal or some sort of engagement to a user based on various criteria. We also help publishers deal with privacy regulations, such as GDPR and CCPA. And we have a simple on-page installation. Much like Google Analytics, you can just take our JavaScript snippet and put on your page, and then everything else you can configure from our interface. We have over 16,000 publishers using the Admiral platform, with over 15,000 events generated per second, and 20 hardworking people working to save online publishing. So over the past few years, the industry has been working to remove third-party cookies from the web. This is because of privacy concerns. And it really started a few years ago with Safari releasing their intelligent tracking platform, or tracking protection. Then last year, Firefox announced their enhanced tracking protection. And earlier this year, Chrome announced that they're going to phase out third-party cookies by 2022. And one of the first steps of that actually just released recently. And now in incognito, they'll be blocking third-party cookies by default. Google released a study that said that ad revenue for publishers could drop by over 50% with the removal of third-party cookies. So publishers are really scrambling here to try and find some solution to get rid of these the necessity to have third-party cookies. And so what they're doing is they're building first-party relationships. They need a way to securely store data for visitors. And some of that data might look like interests, for instance, what is the favorite car brand of a user, whether they're interested in having a baby and they're interested in baby products. Their site preferences, such as whether they want the site in light or dark mode, or even whether they want the homepage to show news versus sports, or maybe their favorite sports team. And also the subscription status for their users, like whether the subscription is active, what tier they're on, whether they, their subscription is delinquent now. And also newsletters. So what newsletters are subscribed to, what newsletters are available, what newsletters they've unsubscribed to. And all this data needs to be quickly available on the page for publishers. Since they're going to use some of this to personalize the site, they need to have it really available before the site can render. So it needs to be there for them very fast. Additionally, based on these subscriptions or different entitlements the user has, they might not even be able to see a particular article because it might be premium content or something that the user needs to pay for in order to view. And also, it wouldn't be very helpful if users that subscribe to a website don't get to access that subscription across platforms or across different devices. So there needs to be a way for this data to be shared across different devices. But unfortunately, most publishers just don't have the development resources in order to build something that would satisfy all of these, let alone maintain it or make sure that it's secure and not leaking private user data. So we built what we're calling Admiral Accounts. This allows publishers to store and access this first-party data using a simple JavaScript API. They can manage user preferences, like I just mentioned, some examples. They can require a subscription, so they can use our Engage platform on pages that are premium to really require that the user has a certain tier of subscription in order to view that content. They can target email engagements or even an ad block ask, like asking a user to turn off their ad blocker based on all of this first-party criteria. And if the user chooses to create a login, the user can then access their subscriptions or their preferences across different devices and platforms. And the publisher, if they have advertising relationships, can store different interests or ask user survey questions in order to store different first-party data to target advertising and increase their efficacy of the advertising that they have on their site. We handle all the password and session management, so password reset, verifying their email, making sure that we securely store the password, making sure that we handle login and log out. We do all of that for the publisher. And we also silo the data per publisher. So a user that gives publisher A data knows that they're not sharing that data with publisher B or even publisher C. And the user is in full control of their data at any point. So if they want to remove, or change certain key value pairs or attributes about them, all that data is open and available to them rather than it being a really opaque process like it is now. So before I talk about the actual problem that we ran into while building this, I want to just give a quick chat about our tech stack. So Admiral is powered by a microservice architecture running on Google Cloud Platform. We have a little bit over 50 microservices at the moment, and it's almost exclusively written in Go. All of our services are available across 5 regions, across 3 continents. That includes Europe, Asia, and North America. And we have over 10,000 HTTP requests per second globally, all with less than 250 VMs. So when we started out trying to build this accounts platform, the problem that we really ran into is how do we make this data available worldwide with single-digit millisecond reads? As I mentioned, some of our publishers are going to be using some of the data that our platform provides them to render their page, so they can't have it taking a long time and make their page respond slower. So it really came down to the database that we decided to choose. Our requirements were that it was obviously highly available and supported horizontal scaling. Some of our publishers have dramatic increases in traffic based on worldwide events, whether there's some sort of catastrophe or whether the president is giving some sort of talk. And so we really had to be able to support those different traffic spikes easily without having to do a bunch of work on our side. Additionally, as I mentioned, we had to have really fast reads. Our goal was less than 10 milliseconds for the 90th percentile. And writes, we were a little bit more conservative about, less than 200 milliseconds for the 90th percentile. The reason being is that writes aren't usually in the critical path or the hot path of a website loading. Those are usually in response to some sort of user action, like a subscribe, or whether they've checked a certain box or saved their settings. So we're okay with those being a little bit slower. But since our team is small, minimal operational overhead was a must. We couldn't have some sort of dedicated person dealing every week with rebalancing or making sure that the cluster was in an okay state. That really had to all happen behind the scenes automatically by the software itself. Because we're dealing with sensitive user data, we had to make sure that we had encryption at rest and encryption in flight. And not necessarily a requirement, but it was really nice to have if the database itself could be flexible for other workloads. So not just storing out this account and related information, but also as we expand our service in the future or even build other microservices, that they could really utilize the same database for multiple things, and we don't just add yet another database to our platform. We also preferred an open source database with contributions welcomed. That would really allow us to dig into the code if we were running into an issue, and also keep an open look at the actual database as it's being built and keep track of things that are happening. On the same wavelength, we preferred there be an open Go driver available and maintained, so we wouldn't have to build that and maintain that in-house. And so the first few databases that we looked at were MongoDB and CockroachDB. We started out with MongoDB because we had a lot of existing infrastructure and code set up with Mongo. A lot of our other services use Mongo, and so we're already kind of familiar with it and had a lot of stuff written already for it, so it was easy to start with. But the problem is that Mongo has vertical scaling. There's a primary that all writes go to, and if you need to scale that, you need to make a larger primary, which means you either need to step down the primary and step up a larger secondary, or something along those lines that requires some difficult operational work. The alternative to that is that you use Mongo sharding, but this introduces the requirement to run Mongos, which is a larger operational overhead. And we had previously tried Mongo sharding for a previous application a few years ago and ran into a few bugs with doing a query on shard boundaries, and cleaning up old shard data after doing a shard split. So we weren't very comfortable with the operational overhead that sharding introduced, and that it would adequately solve our performance and scaling problem. Additionally, Mongo has a document model, which we didn't feel was the most efficient way to store key value information, which these attributes commonly are in accounts. One problem is that if we stored a single key value pair per document, we would be wasting space, and it wouldn't be as fast as storing all the key value pairs in a single document for a user. But then we had the problem where it was difficult to prune and expire data. So if a user's subscription, for instance, expired a month ago and we want to prune that data and remove it, we'd have to loop through all the users and find the subscription key value pair in that array and pop it out and remove it. And that was just more work than we really wanted to do for that. So the next thing we looked at was CockroachDB. It does have horizontal scaling. It is written in Go, which we felt more comfortable with, it being in Go, that we could make any changes, look at the code and understand what's going on if necessary. But throughout testing, we found it had larger instance requirements than we really would have liked. We were hoping to use 4 core, maybe 8 core instances, but that just really wasn't enough for CockroachDB to be usable at the throughput that we really needed. Also, we found it to be unstable at high CPU. We had a few times where instances were running at 50% CPU usage, and we had a small bump in queries, maybe 5, maybe 10% increase in queries, and that all of a sudden jumped the CPU usage up to 100%. And we had to actually shut down CockroachDB in order for the instance to become usable again before we could actually continue the application. Also, cluster unavailability happened twice with the way that CockroachDB does authentication. So when you connect to CockroachDB, you send it a credential, whether username and password or a certificate, and it has to make a request to the primary in order to determine if those credentials are correct. But if that primary is overloaded, those connection requests start to slow down and start to pile up, and then you end up having this stampeding problem where the application can no longer connect, so it tries to make a new connection, and you end up having to just shut down the application, wait for the cluster to calm down, and then start everything back up, which is obviously not okay for us when we're in a production environment. Also at the time, there were no read-only replicas. Since then, follower reads have been implemented in 19.1, I will just mention, but only for enterprise users. So 1.5 years ago, we stumbled upon YugabyteDB. It checked all the boxes for us on our requirements. It has single millisecond reads. Because we could use read replicas in these other continents, such as Europe and Asia, we can hit that local instance without having to touch or go across an ocean to get the data from somewhere else. And the read replicas allow us to have faster write performance because it doesn't have to have a quorum or commit the write across a continent and actually speed up those writes by just having them happen in North America. It has automatic and transparent sharding for easy scaling, so we don't have to worry about manually splitting data or dealing with the shard or tablets as instances go down or up or we do maintenance. It handles all that for us. It's open source, and we've actually already made 1 contribution so far, so that's worked well for us. Also, it has a CQL and SQL interface, so we can really choose the way that we want to store and access the data that's right for the application that we're doing. And this allows us to actually use it for more applications than just accounts or similar use cases. And it supports synchronous and asynchronous cluster replication. We're not using that at the moment, but in the future, we have plans to use it for disaster recovery. And if we want to have a separate cluster that we can do analytics on, or maybe some internal queries that we don't want to affect the production cluster, we can do that and easily set that up as a separate cluster and duplicate it. So how did we actually deploy Yugabyte? As I mentioned earlier, we're on Google Cloud Platform. We have 5 regions across 3 different continents. And we decided to go with 2 instances per region. The reason being, if any single instance goes down, we still have another instance there in order for us to do reads against. We have a replication factor of 3 for the global cluster. And we have 3 masters in the US, 1 per region, along with 1 primary, and then a read replica. So in those, we have 2 instances, a read replica and a primary. The primaries also has a master on it. And then in Europe and Asia, we have 2 read replicas. No primaries in those, as I mentioned earlier, for write performance. And since all these read replicas have the full data set, our application can do secondary reads against each of these local read replicas and not have to worry about crossing an ocean or crossing a continent or anything else to get the data that they need. We deploy it using Ansible on Google Cloud Compute instances using SSD persistent disks. We had tried local SSDs, but we didn't feel like the small marginal performance gain that it gave us actually was worth the operational overhead of dealing with local SSDs. Also, as I mentioned earlier, one of the requirements is that we had encryption at rest and TLS, and we're using both of those with Yugabyte. Also, I want to just give a shout out to the Yugabyte team. They've been a great help over the past 1.5 years at getting us deployed, and any issues we run into, they've been great about helping us on that. So on to implementation. A pretty simple table per data type, so that's sessions, accounts, attributes, entitlements. But we have 2 different unique indexing strategies. So we have 2 application maintained indexes for logins and allocated IDs. The reason being, we don't really do any updates to either of these data types. And so it's okay for us to have the application just manage the index separately, which is really just another table that we call an index, but it's actually just a table. We also have 5 user-enforced consistency indexes. And if you haven't heard the term before, what that means is that when we actually make an update to a table, Yugabyte will do 2 separate commits to update the index and the data alongside each other. But if one of those fails, it will fail the whole update. And it's up to the user to keep retrying that update until it eventually works. And the way that we do that is we use Google Cloud PubSub to push any updates or any inserts that we make into there that affect any of these user-enforced consistency indexes. And we let that retry indefinitely until it finally works, which usually doesn't happen, but in the event that it does for some reason, we have that queue there to make sure that the indexes stay consistent with our data. We're using the Go CQL driver with a connection patch. I posted the link here. The pull request is 1369. All that we did there is make sure that the Go CQL driver allows us to specify that we only care about 1 replica being up before we consider the session started. The default behavior is that all replicas need to be up. But in our case, we could have taken a replica down for maintenance or for updating. And we don't want that to mean that the driver can't connect to the database because that single replica is down. So the change allows us to specify that we really only care about 1 replica when we connect. And as long as 1 is up, we can do reads and we're fine. We also do secondary reads whenever possible, really trying to make sure that 99+% of the time we're hitting that local read replica. And that's how we're able to get such fast performance, which I'm about to talk about next. So on the performance front, we are super happy with Yugabyte. We are blown away by how fast it's able to perform and really just how great it's worked for us over the past year. As I mentioned, we're using the CQL interface with the Go CQL driver. And our 90th percentile reads are 5 milliseconds. So we blew away what our goal was there. And the 50th percentile is actually under 3 milliseconds. On the updates, the 90th percentile update is 230 milliseconds. As I mentioned, that has to cross the US, doesn't go across the ocean, but it needs to cross the US to actually do that update. And also because we have various indexes, it needs to update those indexes as well. But as I mentioned, we're okay with the writes being just a little bit slower. This is still pretty fast, but a little bit slower, just because those usually happen in response to a user input. They're not usually in the hot or critical path of a website. Those are usually where the reads are. So we're okay with that just being a little bit slower on that front. And globally, we have 4,000 queries per second at peak. That really just shows how powerful Yugabyte is and how well it can perform. We're able to maintain the same 5 millisecond read even at that huge peak query level. And we have consistent and equal performance across all regions. So though, whether we're doing a read in Europe, whether they're doing a read in Asia, or they're doing a read in the US, we still have that same 5 millisecond number across all of those. And our application can actually detect stale queries sometimes. And that actually ends up only happening less than 0.03% of the time. An example of that is, let's say that a user has gotten a session ID, and then we go to look up that session ID and it doesn't exist. We can probably assume that the user got a real session ID and that they exist somewhere. It might just not have been replicated yet to the read replica. So we do that query in that case against the primary and determine if it does exist or not. And that actually, like I said, only ends up happening, less than 0.03% of the time. So really 99.97% of our reads are just hitting that local read replica, and that's how we're able to get such fast reads. So we've been so happy with the performance that we're actually looking to move other workloads to YugabyteDB. We have some use cases such as billing and what we call one-click whitelists, which allows a user to click a button and add a site to their ad blocker whitelist rather than having to go through the actual ad blocker menu, that are more relational data. And so those things would be better to be stored in an SQL interface where we can do joins and other things. But we're waiting on follower reads to be available in YSQL. I linked to the issue down here. It's on the roadmap and it's planned and hopefully coming soon, but not quite available yet. But that would allow us to do something similar to what we're doing in CQL, where we have the secondary reads that hit the local replica and really get us that insanely fast speed. We're looking at every workload that we have right now and evaluating where performance is critical. We should probably move it to YugabyteDB and get it off of Mongo. And since we have the background of using Mongo, we like the fact that Yugabyte has support for the JSON-B column, the JSON-B data type, so that if we have any unstructured data that we want to still store in Yugabyte, like we were storing in Mongo, we're able to store that alongside structured data without switching to a different database. And having first-class support for that is just great. So that's it. Thank you, guys. I'm here to answer any questions. Once again, my name is James Hartig, and I'm from Admiral. Thank you.